going on this again. All right. So we were just working on this anyways. So if you had questions, I might have missed them because my whole system froze up there for a little bit. So if you have questions or you go and check your answers for B, C, or D, let me know. All right, so let me go over B. So I'm going to do these a little quicker now. So doing the whole little chart on the side. So B, N-terminus, gly, glue, pro, trip, asp, C-terminus, pH of 7, positive charge, neutral, negative, neutral, neutral, negative, negative. Again, I'm just going from memory on those. So pH 7, charges -2. 1, if you're positive, you stay positive. If you're negative, you go to neutral. So positive, neutral, 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 neutral. So at a pH of 1, we go to +1. 14, it's the opposite. If you're positive, you go to neutral. So NH3 is neutral, neutral, negative, neutral, neutral, negative, negative. 1, 2, 3, that's -3. So that's glyglu pro trip asp. And I'm just gonna rattle through the other ones now. If you have questions, feel free to let me know. So C, we have N-terminus. Then we have asparagine, so N-term, I guess. And phenylalanine is F. Glutamic acid is the cutest, so Q, or glutamine rather. That's not glutamic acid, that's glutamine. Glutamine's a cutie, cutamine. Arginine, everyone's, well, a pirate's favorite amino acid is arginine. A, C-term. 7. So N terms positive, neutral, 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 positive, neutral, negative. So at a pH of 7, this is +1. 1. Positive, neutral, 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 positive, neutral, neutral. So it goes up to a +2. Then pH of 14. Neutral, 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 stays negative, -1. Again, pH of 7 is really your home base for this. This is really how I'm figuring all this out, is that I've learned these at a pH of 7, and then you just go from there. The last one, the image, is kind of hard to figure out when you're not used to looking at amino acids, not used to looking at proteins. So the way to start with this is you need to find the N-terminus. So you need to find the nitrogen that's somewhat open. That is not in two peptide bonds. That's this nitrogen, right? That nitrogen only has one peptide bond. So here we have an amino acid that's coming back on its backbone, so that is P. And then you just follow the backbone. So nitrogen, carbon alpha, C double bond O, nitrogen, carbon alpha. So here's another carbon alpha. So what's coming off this? This is glutamic acid. So continue along, C terminus, N terminus, carbon alpha. Well, here I am wrapped around on myself against this is another P. C terminus, N terminus, carbon alpha. So here we have an amino acid with a branch structure. And that looks like not what I have in my notes, because I have in my notes that's supposed to be threonine, but that's definitely not threonine. That looks like valine. That's valine. That's what happens when you get images off the internet and you don't double check them before you post them. They're not what they're supposed to be. So C terminus, N terminus, carbon alpha. So this is isoleucine, I believe. Then here we have, wow, whoever made this image made it really bad because this is another carbon alpha. And that is not supposed to be there. Well, this image is garbage. And next time I should really make my own images. So if you're wondering what amino acid this was and you're really confused right here, congratulations. You know your peptides quite well because this is not supposed to happen. So I'm just going to say the rest of this is no good. Originally, what this was supposed to spell out was peptide. And I thought I was so clever in doing that. But let's actually do what's on there, which is PEPVI, PEVI. So PEVI, pH 7, 114. Well, I need to put my N terminus in there. N term, PEVI, C term. So P doesn't have a pKa, so it's neutral throughout. E is negative at 7, so that means it'll be neutral at 1 and negative at 14. P, just did that. V, neutral throughout all, doesn't have pKa. I never has a pKa. C, negative at 7. When we get to low pHs, it becomes neutral and it stays negative at high pHs. So PEVI, or PEVIC, -2 at 7, 0 at 1, -2 at 14. All right, so 5 examples here. Any questions whatsoever how I solved any of this? All right, so if not, I'm going to assume everybody has it. And also, I hope you do, because 100% there's going to be a question like this on the test. Make sure you know it. All right, so moving on then. The last thing we need to talk about on this slideshow, and I do believe, I am aware that I had a new slide for today that we haven't got to. That's fine. That's all part of the plan. I know these set of PowerPoint take forever. The last thing we're going to talk about are enantiomers and Fisher projection. So the first thing we have to do is, what's a chiral molecule? So a chiral molecule is a molecule that cannot rotate on its mirror image. So let's remember from organic chem, wedges mean they're coming at you. So they're coming out of the screen into your faces. Dashes mean they're going away from you into the back of your computer. So if I try to take this image on the left and rotate it onto its mirror image on the right, it would be different, because when I rotate this, the molecule that I get looks like this. So they're different. So that means this molecule is chiral. And really, to tell a chiral molecule when it comes to carbon, it's carbon with 4 different groups attached to it, right? So here we have bromine, fluorine, chlorine, and hydrogen attached to our carbon. If that's the case, it's automatically chiral. If you don't have 4 different groups, it's not chiral. So carbon, it's super easy. And when you have chiral molecules, you have what are called enantiomers. Enantiomers are molecules that differ at a chiral center. They have opposite chirality. Organic chemistry, you learned it as R and S. Biochemistry, we call it L and D. And they are not the same things. They are different. And the reason why they're different is because biochemistry and organic chemistry aren't the same field, right? They were studied by different people way back when, and the internet wasn't a thing, so you couldn't share information that easily, so people came up with different systems. And amino acids, well, the amino acids on Earth, 99% of them are L chirality. There are some Ds out there, some D chirality amino acids. They're rare, but we will talk about them this semester. And the advantages to that is that you only have to make one set of enzymes. So enzymes are specific to work on a specific molecule, right? And if that enzyme is working on like a specific set of amino acids, you would need at least 2 copies of that enzyme if both amino acids were found in nature. You need a copy that worked on L amino acids, and you need a copy that worked on D amino acids. In reality, you'd probably need a lot more copies because of all the possible combinations. But to make things simple, life only chose to have one type of amino acid, L amino acids. However, there are other amino acids found, and they are found in what's called the peptidoglycan layer. Glycan. Peptidoglycan layer of bacteria. We'll actually study this, but the peptidoglycan layer is the outer layer of bacteria that's made out of sugar and protein. And the reason why this is an advantage is that one way that we destroy bacteria is by destroying the peptidoglycan layer. In fact, everybody has an enzyme that they produce called lysozyme. It's found in your tears. One place it's found. And what this does is that this will go and cut the peptidoglycan layer, which will kill a bacteria. Well, if we have enzymes that only work with L amino acids, one way to defend against those enzymes is to simply make a D amino acid. Because if you have a D amino acid, the enzymes that work on L amino acids no longer work. It's a good way to defend yourself. Of course, once you do that, once you create the amino acids, then the other organism will evolve so their enzymes can still cut the peptidoglycan layer, which lysozymes still can, even though there's D amino acids. So yeah, it's just evolutionary arms race at that point. But any questions about chiral molecules or enantiomers? All right, so the last thing I have for you is simply tell me if these molecules are chiral. So take a couple minutes, 2-3 minutes, see if you can determine if something's chiral or achiral, and then I'll come back with the answers. All right, since we're running low on time here, let me go through this. So what I do is I try to see, is there a chiral carbon? Because if there's a chiral carbon, the molecule is chiral. So I'm looking for carbons that are attached to 4 different things. This carbon right here is attached to 4 different things. This is attached to a bromine, it's attached to CH3, it's attached to a hydrogen, and it's attached to, what is that? CH3. So 4 different groups. Since there's 4 different groups, that is chiral. Now we go to B. B also has a chiral carbon right here. So that's chiral. C, chiral carbon right here, and also right here. So that is chiral. D, here we have a chiral carbon. So there's also a chiral carbon right here. So that is a chiral molecule. E, this is a chiral carbon. Counted has 4 different groups. So chiral. F, finally, we come to a situation where we are achiral. There is no carbon in here that has 4 different groups attached to it. So that's a achiral molecule. G, same thing. There is no carbon that has 4 different things attached to it. So that would make this achiral. Then H, let's see here. 1, 2. So that has that. That has that. That has that. So H is chiral when you follow along the rings and count the whole ring as a group. Because I can go around the rings each way and they're different, and it's mainly because of this, that makes it chiral. If that double bond O was not there, then it would be achiral. So just a little refresher on our organic chemistry there. The different groups on E, sure. So the one I circled, you have a hydrogen, then you have a chlorine. So coming off here, one direction, it goes CH2, CH2, then CH, CH3, and this is all together, CH3, CH3. Ah, that's horrible. Let me rewrite. So that direction is CH, CH3, CH3. If I go the opposite direction, it goes CH2, then it goes CH. Oh, there is no CH. That's just carbon. I don't know how to count. CH3, CH3, then CH2. Basically, when it comes to rings, the trick is you go around the ring and you just ask yourself, is the path, or do I run into the same things along the ring? What I mean by that is, let me get rid of all this nonsense. If these things weren't here, then going this way and going this way, you run into the same thing. Go to left, I hit CH2, CH2. So 1, 2, 3. I hit 4 CH2s till I'm back at the start if I go from the left. And I do the same thing if I go to the right. So that would be achiral. But the way it's laid out right now, if I go to the right, I hit a CH2, then I hit a carbon attached to a bunch of things. If I go to the left, I hit a CH2, CH2, then I hit a carbon attached to different things. So that makes each side uneven, which makes the ring chiral. So that's what you need to look for when it comes to a chiral ring. Find a carbon and see, depending on which way I go, are these things different? Do I get different pathways? And it also has to have a group attached off of it. It can't, so even if you go two separate directions, if it's H and H, like it's not chiral. So for example, this carbon is not chiral that I just drew because it has two hydrogens attached to it. So remember, 4 different groups on my carbon. There are other ways to determine it. In organic chemistry, you probably learned about planes of symmetry. I don't know. I just don't use those myself. I can look at a molecule and determine if there's 4 different groups. If you like the plane of symmetry, what that means is if you look on F, I can draw a dotted line across it and then fold it up, and it's the same thing. It's the same molecule on each half. So that's another way to tell if it's achiral. But we're not, yeah, this isn't a big concept for us. There'll just be maybe 1 or 2 questions on the test to determine if something's chiral or not. Yeah, G should be. And the reason is there's no chiral carbon because there's no resonance structure really. The way those double bonds are handled, every single carbon has a double bond attached to it. And because every single carbon has a double bond attached to it, by definition, it can't be a chiral carbon. And so I was actually doing that one earlier because it looks like it should be chiral, but the problem is if you try to draw resonance, so let's say like I did a resonance structure here, and then this carbon came up, then this carbon would lose a hydrogen. I mean, you could say that like, okay, if that happens, then this moves over there, this moves over there, then this carbon only has 3 bonds. And the resonance structure is not going to allow for a carbon that really has 3 bonds at a time. It's going to be very, very unfavorable. So yeah, based on no chiral carbon, it's not a chiral molecule. That would be able, you'd be able to flip it on its mirror image because everything, because double bonds will make everything flat. That's going to be a relatively flat molecule. Unlike what we saw in the previous picture. In the previous picture, right? When you have carbon attached to 4 different things, you get things that, because it's tetrahedral at that point, you have things coming at you. You have groups coming at you and groups going away from you. Once you lose the tetrahedral structure, and you lose your tetrahedral structure by having a double bond, when you have only 3 groups attached to carbon, that's going to be in a plane. You're not going to have groups coming at you or going away from you. That's in a plane. So I can even make this one CL. So when I flip this like that, and I can rotate this to fit on my mirror image. Because if I rotate this, and it's hard to do on a 2D surface. I don't have a model kit with me, or I would show you that way. But you rotate that 180 degrees, since you don't have groups going out of the page or into the page, it can fit right on its mirror image. So that's the problem I see with G. All right, any other questions? Right. Well, it's 3 o'clock. And it's the end of this PowerPoint. So we will continue on Wednesday. Remember, test next week, Friday. I'll put a homework up like always. And if you have other questions, don't hesitate to email me. And I will see people later. Have a good day, everybody.